Hey y'all, we are Memphis Communiversity and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. Today we're going to be continuing our area and volume unit and we're going to be doing the most important lesson of them all, volume by revolution and rotation. So what's going to happen is that we're going to have a 2D region, we're going to spin it around a rotation axis, we're going to try to imagine the solid that's formed by rotating it around this axis, and we're going to find the volume of that solid. So keep in mind that this is going to be a high school level, so we're not going to be doing cylindrical cells. We're just going to be doing disc and washers. So the first half of this video will be talking about this. The second half of this video will be talking about washers. Keep in mind that this video might be a little lengthy, like some of our videos, because we have a very specific process, and this process does take a little bit of time to explain. But hopefully once you sort of nail down this method and you know the steps pretty well, you're going to be able to get every single volume by rotation question correctly, because it's the same thing over and over and over and over again. So keep in mind that throughout this video, we're not going to draw the 3D shape, or we're going to try to not draw the 3D shape. We feel like it's unnecessary, and I don't know how to draw 3D shapes basically, but you can get the questions right with just the 2D shape. Another thing we're not going to be doing is we're not going to be computing integrals in this video, because we want to focus on setting up the integrals that give you the volume of a solid as opposed to actually computing the integrals. On the AP exam, you could potentially type this in a calculator or maybe even leave it as the answer. That's what usually happens. So again, let's just go through this method of volume by rotation. We're going to do this first, we're going to write out steps, and we're going to do a few examples, and then finally we're going to do washers, which are a little bit trickier, write out steps, and then do a few examples. So let's get started. So let's talk about the steps for this first. And again, this might not make any sense until we do real examples, but I want to write out the steps first. You can write them down on your paper, whatever you're taking notes on, and then as we do the examples, you can consult them. So steps for rotation by this. So rotation by this. And of course we're doing volume. Probably should have put that word first. But first off, always the givens in these questions is going to be a region, and then it's going to be a rotation axis. So you're not going to be able to choose the region, you're not going to be able to choose the rotation axis, those are given for you. So the first thing to do is just note the rotation axis. So we have a rotation axis, and there's going to be two types of rotation axes, I guess. The first one is going to be a horizontal line, mainly the x-axis, but also lines like y is equal to 3. And then you have the vertical lines, something like x is equal to 2. So when you have a horizontal line as a rotation axis, it's going to look something like this. Again, it's horizontal. And what we're going to do is we're going to draw a dx rectangle. So if you saw the area video that we did previously, we appreciate it, but it's sort of the same thing. I like to draw this dx rectangle. It'll help me form the disk, and it also helps me remind myself that everything has to be in terms of x's when you are doing this sort of axis. The other type of rotation axis is vertical. So it's going to be vertical. Again, this will be given, like you don't get to choose the rotation axis. And we're going to draw this axis, and then we're going to label this dy, because it helps me remind myself everything has to be in terms of y. So that's going to be step 2. Step 2 only occurs in certain cases, but if you have a dy rectangle, what you want to do is change everything to be terms of y's. So if it's a dy rectangle, then everything needs to be y's. And you'll see an example of this, but for example, if you have the function y is equal to x squared and you need to change it to y's, it's going to be x equal to the square root of y. What we're going to do is we're going to convert our function to be in terms of y's, because we can only put y's in the integral because we're integrating with respect to y. So that step 2 only occurs if you have a dy rectangle. So step 3 is going to be try to draw the disk. Draw the disk. And the important thing about this disk is that the radius of this disk is going to be the top minus bottom of this rectangle. So the radius of this disk is top minus bottom of rectangle. Either the dx rectangle, and if you're doing y's, of course, just like our area question, area videos, it's going to be right minus left instead. So if we have a dx rectangle, it's going to be top minus bottom. Literally, what is the top of our dx rectangle touching? Literally, what is the bottom of our dx rectangle touching? And if it's vertical, it's going to be right minus left instead. So the last thing what we're going to do is we're going to write the answer. So the volume is going to be the area, not the area, but the integral of the area of this disk. So it's going to involve pi's because the area of the disk is going to be pi r squared. So for example, what it's going to be is going to be either a to b of top minus bottom. So we can write t minus b squared because that's going to be the radius when we are doing dx rectangles. We're going to have a pi in the front. Or if it's a dy rectangle, it's going to be right minus left instead. So it's going to be c to d, right minus left instead. So it will be either this one or this one, depending on if you have a dx or dy rectangle. Just like with the area questions, you do have to determine the endpoints, but the endpoints will be given by the region. It's the leftmost x value and the rightmost x value, so a to b, or if it's the bottommost y value and the topmost y value when you're doing y's. So this is the process, and then this will be the answer. Again, we're going to end after this integral. So let me just run through this and we'll do actual examples. So the first step is the rotation axis, horizontal axis, we're going to draw a dx rectangle, vertical axis, we're going to draw a dy rectangle. If it is a vertical line here, if we do a vertical rectangle, meaning a dy rectangle, sorry, if we have a vertical axis and we have a dy rectangle, so notice that depending on the rotation axis, your rectangle is going to be perpendicular to your axis. So if you have a horizontal axis, you're going to have a dx rectangle. If you have a vertical axis, you're going to have a dy rectangle. Hopefully I didn't contradict myself earlier, but that's what it is. So then when you have a dy rectangle, you're going to see that we have to do a little bit more work. We're going to have to change everything to be in terms of y's, and then my integral is going to have dy in it. Finally, we're going to draw the disk, and the disk is, the important thing about this disk is that the radius is going to be top minus bottom of a dx rectangle, or right minus left of a dy rectangle. Finally, when we take the volume, just like area is the integral of the vertical distance, when you sum that dimension lower, you're going to get that dimension. So the volume is going to be the integral of the area, and the area is going to be top minus bottom squared pi, because this is the radius, pi r squared, or pi r squared right minus left. So let's try to see this process in action, because it's harder to talk about the steps without knowing any examples. So let's go for them. So let's do this. So our first region is going to be bounded. So R is bounded by the y-axis, the line y is equal to 9, so the horizontal line, you can say the horizontal line, sometimes they give you that information that it's horizontal. But remember that horizontal lines are y is equal to a number, vertical lines are x is equal to a number. So we have this region bounded, and then we have a function, it's going to be y is equal to x squared. So I'm going to draw a little picture here. This is the function y is equal to x squared. Keep in mind that in these questions, usually they give you the function or the graph, and if they don't, you can type it in a calculator. But it looks like this is our region here, so notice that this is our arc. This point right here, which will be important, is going to be 3, 9, because 3 squared is 9. It's often good to find your intersection points when you do these questions. So my question is, we have this region, and what we're going to try to do is, this may be shark fin sort of shape, and what we're going to do is we're going to try to spin it along the line y is equal to 9. So what we're going to try to do is we're going to try to find the volume of the solid by rotating it along around the line y is equal to 9. Around y is equal to 9. So keep in mind, again, we're not drawing a 3D shape, but if you want to picture this, what we're going to do is we're going to take this region right here, and you're rotating it. Imagine that this is sort of a string, and you're just rotating it really, really fast along this axis. Notice that you're going to get some sort of vertical bowl shape, where the bowl is like open up here, so it's going to be bigger over here, and then it's going to be smaller over here. But again, if you don't want to think about it at all, you don't have to draw the 3D shape. You can just do it based off this. So first off, we're just going to run through the steps. The first thing to decide is a dx rectangle or dy rectangle. That decision is very easy. Because we're rotating around y is equal to 9, that's a horizontal line, this is going to be dx rectangle. So I would like to draw a rectangle basically arbitrarily in the region, and then we're going to have a dx rectangle. Keep in mind that in this case, the dx rectangle is touching my horizontal axis. Notice the top of the rectangle is touching the horizontal axis, the axis I'm rotating around. So in this case, we are going to have a disk. There's no space in between our rectangle and our axis. What we're going to see in washers is that there will be a space, and that space is very important. But for now, we're going to be doing this. So now that we have this axis, because we don't have a dy, all we're going to do is we're going to start drawing the disk. So we have this. Again, a little bit of a theory. So imagine you have this right here and you take this marker and you spin it around. If you notice, you're going to have some solid circle, and that's what the disk is. And if you're able to stack up a bunch of disks, sort of like a stack of plates or something, you're going to be able to form a 3D solid. So that's what we're trying to go for. But again, the method is more important than what we're actually going for. So what we're going to try to do is we're going to try to find the area of this disk, meaning a solid circle, when we spin this around. So think about this as the radius. And remember that it's pretty easy. The disk radius is just top minus bottom. So what we're going to do is we're going to look at the top function. So if you label this function as y is equal to x squared, it goes over here as well, but because we're bounded by this is our region. So if you look at this region right here, all we're going to do is top minus bottom. So you look at the top of the rectangle and you see what is it literally touching? It's touching this line right here, so it's going to be 9. So that's going to be 9. Finally, what is the bottom of this rectangle touching? Well, it's literally touching the bottom function here. That's going to be x squared. So it's going to be 9 minus x squared. So that's going to be my radius, and now we're basically done. We're going to form an integral. Once you have the disk, all you have to do is integrate pi r squared, but you already found r, so we should be good to go. It's going to be pi, and then r is going to be this, 9 minus x squared, because it's r squared, where r is this. And then finally, we do have to choose coordinates, but because we're dealing with x values, what we're going to do is we're going to look at the leftmost x value. In this case, it's going to be 0. Over here, it's going to be 3, so it's going to be 0 to 3. And this is the answer for the volume. We're going to leave it like this for every single question, because we're not going to focus on the integrals, but you could type this in a calculator if need be. But this is how you do integrals by disk. Let me just go over the process briefly. So you have your region, usually that's given for you, and what you need to do is you need to determine if you have a dx rectangle or a dy rectangle. In this case, it's a dx rectangle because we're rotating around a horizontal line, and the dx rectangle is perpendicular to that horizontal line. What's happening is that we're spinning everything around, but you don't really need to know that. All you have to know is that you're going to be forming a disk when you spin around this little rectangle. So what I want to do is I want to find the area of that disk. In order to find the area of that disk, I need the radius of that disk. But the radius is pretty easy. All it is top minus bottom of this rectangle. So in this case, it's going to be 9 minus x squared. Then you start forming your integral. Your integral is going to be pi r squared. You already found the radius. You already did the hard work. So it's pi times top minus bottom squared. And that's all it is. You do have to choose coordinates on the integral. It's not based off the rotation axis. Be careful about that. It's all based off the region, just like our area question. So in this case, it goes from 0 to 3. And that's our answer. So let's try to do a few more of these, or maybe several more of these, just to get the hang of it. One more disk question, and then we'll move on to washers. So let's say we have the same region. So we're going to have the same region. So let me erase just a little bit of it. So let me retrace over this line. But instead of rotating around the line y is equal to 9, now we're going to try to rotate around the y-axis. So keep in mind that the y-axis is, of course, a vertical line. So even if we have the same region as the previous question, rotating it around a different axis totally changes the question. So in this case, what we're going to do is we're going to rotate around this line right here. So notice that when we have this region and you rotate it, you're going to form some sort of bowl, and the bowl will actually irregular this time. If you want to draw the 3D picture, we'll just draw it briefly. It's going to look something like this, where we're rotating this region right here around this axis. But again, I feel like when you answer these questions, you don't need to know what the resulting solid looks like. Let's go for the steps. So because we're rotating around the y-axis, you draw a dy rectangle, because you always want your rectangle to be perpendicular to your rotation axis. So it's going to be a dy rectangle. So we can label this dy. Keep in mind that we should pause here. This is step 2. Unfortunately, dy rectangles do require a little bit of work. What we need to do is we need to write this function in terms of y's instead of x's, because we don't want to call this x squared, even though this function is x squared, because all of our integral has to be in terms of y. So what I'm going to do is I'm going to solve for x in terms of y so that I can use that instead in my integral. So what is y is equal to x squared? How do I convert that? That's going to be x is equal to the square root of y. So that small step is necessary, and now we're ready for the disk. So because we're dealing with a dy rectangle, our disk isn't going to be top minus bottom. That's not going to be the radius, but it's going to be the analogous sort of thing in the context of dy rectangle. It's going to be right minus left instead. So what's the right function? Again, the right function is this parabola, but I don't want to use x squared because, again, I want everything to be in terms of y's. So there's two names for this function. I used this one when I was doing the dx rectangle, but because I have a dy rectangle on my hand, the right function, dy, I'm going to use square root of y instead. So again, it's right minus left when you're dealing with a dy rectangle, but you want to use the things in terms of y. So it's going to be square root of y. Finally, what is the left of this rectangle touching? The left of this rectangle is touching right here. It's touching the y-axis. What's the y-axis? That's the line x is equal to 0. So in this case, it's going to be just right minus left, where 0 is actually the left. I like to still write right minus left, no matter if it's 0 or not, because I don't like to simplify things, and I like to do the same thing every single time. So we should be ready for the answer. Once you have the radius, you've done all the hard work basically. What you need to do is you need to form your pi, and then you're going to have radius squared, pi r squared. You're always integrating the area of the shape, so it's going to be pi r squared, but this is r, so it's going to be square root of y minus 0 squared, right minus left squared. And again, remember that you do need to focus on the numbers. The numbers are going to be dependent on y's this time. So what's the bottommost y value? Well, it's going to be 0. What's the topmost y value? It's going to be 9. So it's going to be 0 to 9 as opposed to 0 to 3 for the x's. But those are the stops. Hopefully that makes sense. Again, when you have a dy rectangle, and we're doing a dy rectangle, we were forced to, maybe against our own will, because we are given a solid that we're rotating around the y-axis. You always draw a rectangle perpendicular to your rotation axis. So in this case, it is a dy rectangle. So once we have our dy rectangle, the first thing we did is we converted our functions to be in terms of y's, because everything has to be in terms of y's. Then we formed our nice disk here. How do we know that it's a disk? Well, again, notice that this rectangle is literally touching the axis that it's rotating around, no matter where you draw it. We'll see examples in the next one where we're going to start our washers, where the rectangles are not touching this axis. But if it is touching this axis, that means you have a disk. So it's going to be right minus left, not too bad. Right minus left, where we use the y name for the function. And finally, we form the integral pi r squared, where r is right minus left. And then we go from the y coordinates. So always in these disk questions, if it's a dx rectangle, it's going to be pi integral top minus bottom, all of that squared, and you're going to choose x coordinates. For y's, it's going to be pretty similar. It's going to be pi integral right minus left instead, all of that squared, and then I guess square would be over here maybe, and then y coordinates. So those are how you do disk. Disks aren't that bad, even washers aren't that bad, but let's see the difference between disk and washers. So now I'm going to do the washer steps just like I did with the disk steps. So let's erase this. So now let's go for washers. So rotation, volume by washers. So a lot of these steps are going to be the same, but there's going to be a few added steps. So step one, it's still based off the rotation axis. We'll call it rod axis. And if it's horizontal, it's still going to look like this. You're going to still draw a dx rectangle, but what's going to happen is that there's going to be some space between the dx rectangle and the axis. So we're going to have some space here. So we're going to have a dx. Or if it's a vertical line, there's going to be some space between the rectangles. This is what makes this a washer as opposed to a disk. So what we're going to do though is we are going to add a connector from our disk, or from our rectangle to our rotation axis. So again, how we know that it's going to be a washer and not a disk is that there's going to be some space in between the rectangle and the axis, no matter if it's horizontal or vertical. So this is our horizontal guys, these are our vertical guys. And what we're going to do is we're going to draw a connector line segment from our rectangle to our axis, no matter if the axis is above or below the rectangle. So that's going to be that. This is going to eventually be the inner radius, as we'll see. So in step 2, what you do is you do the same thing as in your disk cases. If you have things to be in terms of y's, you need everything in terms of y's. So if you have that dy rectangle. So if you draw a dy rectangle, just change everything to y's. You might as well, you're going to have to do it eventually. So change to y's. So that of course doesn't happen with a dx rectangle. So step 3 is going to be draw a disk instead. Not draw a disk, draw a washer instead of a disk. So what's going to happen is that you're going to have some sort of washer like this. So a washer means like those little washer things. So the point of this washer is that, again, we want to find the area of this washer because we're going to be integrating the area of the washer in step 4, just like we integrated the area of the disk in step 4 when we were doing disk. So in this case, we need to find the area of the washer. Unfortunately, the area of this washer, so we're trying to find this thing right here, this area, but it is going to be 2 circles. So what we're going to do is we're going to find the area of the outer circle and subtract the area of the inner circle. And to find the area of both of these circles, what we need to do is we need to find the radius of both of the circles. So the outer circle is going to be top minus bottom of something. And the inner circle is going to be top minus bottom of something. So maybe we can call it inner radius actually. So inner radius. Or right minus left, of course, if you're doing y's. So the question is, what is it the top minus bottom of? Well, if we have this picture right here, it's going to be pretty easy. So the outer radius is going to be top minus bottom of your rectangle and your connector line segment. So just think of this as one single object, the rectangle and the connector line segment. So it's be top minus bottom of the rectangle plus this connector. We can write connector. The inner radius is just going to be the area of the connector, or the length of the connector. So top minus bottom of the connector. And again, this is going to make a lot more sense when we do examples. So it's a little bit different than this because we have 2 radii. The outer radius is top minus bottom of the rectangle and the connector. So this entire thing as one single object. Literally what's the top, literally what's the bottom. And then the inner radius is going to be top minus bottom of just the connector. It's never top minus bottom of the rectangle itself, unlike the disk. So once we have this information, you're going to be able to find the answer. So the answer is going to be 4. It's going to be volume. Just like before, we're going to have a pi because the formula is pi r squared minus pi r squared. So it's going to be pi integral of a to b. And what it's going to be is the outer radius minus the inner radius. So outer squared minus inner squared. And again, this is pretty complicated, but before we go, let me just tell you, the outer radius, again, is going to be top minus bottom of the rectangle and the connector as one single object, and the inner radius is going to be top minus bottom of just the little connector. So keep in mind that sometimes when people form this formula, they form it wrong. They do it outer minus inner squared, but in fact, it's going to be outer squared minus inner squared because it's going to be one circle minus the area of another circle so that you can find this region as we want, the area of this region. So this is going to be the setup. Of course, if you're doing with dy's, everything remains the same, except everything has to be in terms of y's, and you're doing right minus left instead. So if we draw a dy rectangle, we're going to change to y's, and when we do the washer step, the outer radius is still the same, but it's going to be right minus left of the rectangle and the connector. The inner radius is going to be the same, but it's going to be right minus left of the connector, just the connector. Finally, when we form volume with the dy case, it's going to be pi times integral of outer squared minus inner squared. Still the same thing, where outer is going to be right minus left instead of top minus bottom of something. Again, with the same thing with this, we do have to focus on the numbers themselves. We have to be consistent with them. And if we're doing dx rectangle, immediately, well, we're going to use x's. And if we have dy rectangle, we're going to use y's. So let's see this in action as well. So let me erase this. The steps might seem pretty complicated, but again, if you sort of follow this method, if you watch these steps through these examples, you should be sort of mastered all these questions. So the first one I'm going to do is the region is going to be bounded by y is equal to x squared, and then y is equal to 2x. So let's draw a region right here. So x squared looks like this. It goes over here, but because 2x sort of bounds it, we can draw the line 2x. So these functions, of course, go forever, but this is going to be my region right here. So what we need to do is we need to find these points of intersection. Usually you might have a calculator to find these points. You might type it in a calculator using the graphing functions or using the solve button. But in this case, we're just going to list them out. It's a pretty simple line and parabola. So it's going to be 2, 4, and 0, 0. So this is my region in question. And what we're going to do is we're going to take this region and rotate it around various axes. So my first one I'm going to rotate it around is the line y is equal to 0. Let's do the x-axis first. So we're going to find the volume where we rotate around the x-axis. So keep in mind, again, always in these questions, the givens are a region. You don't get to choose the region, it's just right here. And also the rotation axis, and the rotation axis dictates the question, just like the previous one. So in this case, this is my line y is equal to 2x, it looks like. And this is my line y is equal to x squared. So let's go for this. So rotating around the x-axis, well, that's a horizontal line, so automatically I draw a dx rectangle. So the dx rectangle is going to look something like this. It's within my region. But notice, unlike our disk examples, there is a space between the rotation axis, which is way down here, and the dx rectangle. So what I'm going to do is I'm going to connect it with this line segment. So this is going to be my picture. Again, this dx rectangle only fits right here. I need it to connect all the way down to my rotation axis, so I draw this little connector. And what I'm going to do is I'm going to spin this rectangle around just like with my disc, but when I spin it around, because there's space between the rectangle and the axis, we're going to be forming a washer. Notice that if you spin this around my arm, and I spin it around, spin it around, spin it around, there's going to be this space, which is what is formed by the washer. Think about a washer as a flat donut, basically. So now that we have this, we can start going for our washer. So I like to draw the washer. Potentially, if you get good at this, you're not going to draw the washer, but for now, I'm going to definitely draw the washer. And remember that it's just slightly harder because you have 2 radii, but it's not that much harder because you just need to know how to form each radius. So I like to form the inner radius first because the inner radius first only deals with the connector, so the inner radius. What it is top minus bottom of just the connector. So here is the connector between my region and my axis. So just literally look at what the top and the bottom of the connector is touching. So what is the top of this connector touching? Well, it's going to be the line x squared. So it's going to be x squared. So top minus bottom of connector. We'll put connect. So it's going to be x squared. And then what's the bottom of this line touching? Well, it's going to be the x-axis, which is the function minus 0. So it's going to be top minus bottom. So before with this, we were doing top minus bottom of the rectangles. Here with the inner radius, we're doing top minus bottom of just the connector. Now we're going to do top minus bottom of the outer. So outer is again a top minus bottom. And when you want to think about this top minus bottom is that it's the top minus bottom of this entire object where you perceive this as one single object. Both the rectangle and the connector as one single object. The top of this entire object minus the bottom of this entire object. So it's top minus bottom of the entire object. So still, you're literally looking at what's the top of this function touching. So it looks like it's touching the line 2x. And then what's the bottom of this function touching? Well, it's touching the line, the x-axis. So again, it's going to be minus 0. So take a little bit of pause to form the washer because just like with the disk, once you have your washer drawn, you're going to be able to form the integral pretty easily as long as you understand the method. But let me just repeat, and we're going to do more examples of this with this region. The inner is always top minus bottom of the connector. The outer is top minus bottom of the entire object. So top minus bottom of the connector, top minus bottom of the entire object, top minus bottom. So now we're going to go for the volume. So V stands for volume, and the formula is pi integral, and then you do outer squared minus inner squared. But if you already drew your washer, all you have to do is substitute what your radiuses are. So in this case, it's 2x minus 0, so it's going to be 2x minus 0 squared. And then what's the inner? It's going to be x squared minus 0. So that's that. We do have to choose if we want to go from x coordinates or y coordinates. Should we go from 0 to 2 or should we go from 0 to 4? Keep in mind that this is not relevant from the rotation axis. It's all based off of the region points. And in this case, because we're dealing with dx's, we're going to put 0 to 2. So that's how we do our first washer question. We're going to leave the answer like this. So again, I don't think they're too bad. First off, let me just go over the steps and we'll do another one. We're rotating around the x-axis, so we immediately draw a dx rectangle. We notice that there's space between the dx rectangle and the rotation axis, but we don't panic. All we do is we connect it. Then we go for our washer. When we're going for our washer, I like to do enter first. Enter is top minus bottom of just this phantom line connector that we drew that was not part of the region. So it's just the top function minus the bottom function. Outer is a similar thing, but it's top minus bottom of the entire object, the rectangle and the connector as one perceived object. So top minus bottom. So then once you have outer and inner, all you do is you take pi integral of your x coordinates because you're dealing with x's, and then you put outer minus inner, and that's all it is. So let's try to do another one. Maybe you can do this one as practice, and we'll talk about it. We're going to have the same region, and we're just going to rotate it around a different axis. Of course, the given rotation axis highly affects the question. So let's erase this. And let's rotate. So I'm erasing this. So let's rotate, instead of around the x-axis, let's rotate around the vertical line y is equal to 4. So this is not a vertical line, a horizontal line actually. Sorry about that, but it's the horizontal line y is equal to 4. Remember, y is equal to a number infers that it's going to be a horizontal line. So let me erase this a little bit so that I can write the function a little bit. So this is still y is equal to 2x. Just this simple line. So now we're rotating it around the line y is equal to 4. So let's just try it. If you want, you can try this for yourself. Pause the video, and in 3 seconds, 3, 2, 1, let's go for it. So hopefully you had a chance to do this, but we're just going to go through the steps, of course. Because we have a horizontal axis, we immediately draw a dx rectangle. We are forced to draw this rectangle. Then we notice that there's space between my dx rectangle and my rotation axis, so I'm going to connect it with the connector. Once you have this, now you're ready to go for the washer actually. So we're going to draw a nice washer, meaning it's 2 concentric circles. We need to find both the radius of each of these circles, the inner radius and the outer radius. So inner and outer. Keep in mind that the inner is always top minus bottom of just the connector. So here's our connector. We're literally looking at top minus bottom. Keep in mind that this is the line y is equal to 4. So what's the top of this connector touching? Well, it's going to be the line 4. What's the bottom of this connector touching? Well, it's going to be this line right here, which is 2x. So in this case, the inner is going to be 4 minus 2x. Again, it's top minus bottom of just the connector. Then when we do outer, we're going to do a similar thing. It's going to be top minus bottom of something else, but it's going to be of this entire object, the connector and the rectangle perceived as one object. So it's going to be top minus bottom of the object. So let's literally see what the top of this object is. And even if it's upside down than the previous one, I literally mean top by what is the top of the thing, like what is the highest thing. So here top is going to be the line y is equal to 4. And then what is the bottom of this entire object touching? Well, it's going to be touching the parabola, which is going to be x squared. So it's going to be 4 minus x squared. So hopefully you got that. Again, inner is top minus bottom of just the connector. Top minus bottom of the entire object is the outer. Once you have that, you should be good to go. It's going to be pi integral. Because we're still doing a horizontal axis, which forced me to draw a dx rectangle, it's still going to be in terms of x's. So it's going to be 0 to 2. And then finally, it's outer squared minus inner squared. If you drew the washer, we should be good. Outer squared minus inner squared. And that's it. Keep in mind that it's not outer minus inner squared because we're doing 2 circles subtracted from each other. But that's the process. Hopefully you see that it's not that bad. You draw your dx or dy rectangle depending on the axis. You connect it. Then you draw your washer. The connector radius is going to be top minus bottom of just the connector. And then the outer radius is top minus bottom of the entire object. Finally, you form your integral. Pi times integral outer squared minus inner squared. So now let's do this same region and let's do it one more time with a vertical axis so that we can practice with vertical axis. So let me erase this. So we're going to erase this. We're not going to erase this region. We might need to eliminate some of these lines. Keep in mind that sometimes they ask 2 rotation questions and 3 response questions. So if you're doing these questions, it's nice to erase your dx and dy rectangle because potentially you might have a different question in the next one. So in this case, what we're going to do is we're going to rotate around the y-axis this time. So around the y-axis. So again, rotating it around the y-axis will highly affect the question, especially because now we're doing something vertical. So because this is the y-axis, just like with our disk, what you do is you draw a rectangle perpendicular. So we're going to do our first dy rectangle for washers. Just like the previous examples, there's some space between this rotation axis and the rectangle that we drew. So this is going to be a washer and not a disk. So we're going to connect this. Then we have to unfortunately change everything to be in terms of y's, because when we plug in these functions, we need everything to be in terms of y's because we're integrating with respect to y. So instead of calling this parabola y is equal to x squared, I'm going to call it x is equal to the square root of y. I solve for y. Same thing with this one. Instead of calling this line y is equal to 2x, I'm going to call it x is equal to y over 2. So now that we have everything drawn, we should be ready to go for the washer. So let's draw the washer. So it's our washer. Keep in mind, of course, that for this washer, we're going to have everything in terms of y, so we need to do right minus left instead of top minus bottom. But let's do the inner just like normal. So the inner radius I like to do first. So it's going to be right minus left instead of the connector. So in this case, what is the right of this connector literally touching? Well, it's going to be this line, but we're not going to use y is equal to 2x. We're going to use x is equal to y over 2. This line does have two names. We use the x name when we're dealing with x's. We're going to deal with the y name when we're dealing with y's. So it's going to be y over 2. This is the right. What's the left of this connector touching? Well, it's going to be the y-axis. That's just the function 0. So it's going to be y over 2 minus 0. I still like to write minus 0 because I like to write right minus left. Then we're going for outer. So outer is going to be right minus left of the entire object. So this connector and this rectangle perceived as one object. So everything is just reversed from dx's, but it's still the same thing. Top minus bottom of just the connector, top minus bottom of the entire object, or right minus left of the connector, right minus left of the entire object. So in this case, what is the right of this entire object touching? Well, it's going to be the parabola, and I'm going to use the y name for the parabola, so it's going to be square root of y. Finally, what is the left of this rectangle, this entire object touching? That's going to be the y-axis, so it's going to be the function square root of y minus 0. Just like with the dx rectangles, once you have this information, the answer should be pretty easy. It's just going to be volume equals the integral. We're not going to forget a pi. Then one thing we have to do is we have to remind ourselves everything has to be in terms of x's. So instead of going from 0 to 2, like the previous examples, because we had a dx rectangle, now that we have a dy rectangle, we're going to go from the bottommost y to the topmost y in the region. So it's going to be 0 to 4. Keeping in mind that the rotation axis does not affect the numbers, it just affects which numbers you choose. But the actual number that itself does not affect the numbers. It's all dependent on the region. So it's going to be 0 to 4. Then we're going to do outer squared minus inner squared. And even if we were doing right minus left instead of top minus bottom, it's still the same thing. So right minus left, this goes here. This was the outer, the entire object. And then the inner was just the connector. So it's going to be y over 2 minus 0. And then we do have squares. Outer squared minus inner squared. So that's how you do washer questions. The process is the same thing every single time. You draw a rotation axis, you draw your washer. Inner is top minus bottom or right minus left of just that little connector that you drew because there was space in between the rectangle and the rotation axis. And then your dx rectangle, your outer radius is going to be right minus left or top minus bottom of that dx rectangle or dy rectangle. And then once you have that, you're able to form the volume formula, pi times the integral of outer squared minus inner squared, where again, inner is dependent on just the connector, outer is dependent on the entire object. So that's how this works. Let's do one more example where it's a little bit trickier. Maybe you'll think it's trickier, I'm not sure. So let's erase this. So we're going to have one more new region. So our region is going to consist of the x-axis. That's going to be one of the boundaries. The other boundary is going to be the function y is equal to the square root of x. And then the last one, I believe I want y is equal to minus x plus 6. So let me draw a brief picture of this. It's going to look like this. It's going to be square root of x. And then it's going to be the line negative x plus 6, which will be like right here. This point, which is very important, the intersection point, again, if you have a calculator, perhaps the first thing to do is just find this intersection point. This point right here is going to be 4,2. Because notice that the square root of 4 is 2, and negative 4 plus 6 is 2. This point right here is going to be 6, 0, because negative 6 plus 6 is 0. And then this is going to be the line negative x plus 6. And this is the line y is equal to the square root of x. So hopefully you can see our region. I already labeled this guy right here, so we'll just label it once. Y is equal to the square root of x. So hopefully you see that this region R is going to be this. And what we're going to do is we're going to rotate, find the volume by rotating this nice region around not the line x-axis, but we're going to do one a little bit below that. We're going to rotate around a horizontal line. Y is equal to negative 2 or something like that. So in this case, the rotation axis is going to be below. So we're going to still go for the process, but the problem with the process is that top and bottom change. And if you remember from our area video, if top and bottom changes, it's not the worst thing in the world, but you just have to do 2 separate questions basically and add the answers in the end. So notice that we still draw dx rectangles because we have a horizontal axis. Also, we are doing a washer because there's space between our rectangle and the axis itself. So we're going to connect it using our connector. But notice that over here, the top and the bottom is going to change because the top will now be this line as opposed to the square root function. So what's going to happen is we're just going to think of this as 2 different questions. We're going to do the same process that we've been discussing in the past for this half of the region with this function, and then we're going to do it again for this region. Keep in mind that if the top and bottom ever changes, no matter if you're doing area or volume by revolution or rotation, or even our next video, volume by cross-section, you just have to do 2 separate integrals. But it's not going to be too bad. Nice last way to practice. So now that we have everything drawn, we have our dx rectangle, we have our connectors, let's draw 2 little washers. So let me draw that. So washer, so this is going to be my inner, and this is going to be my inner as well. So let's draw this. I don't usually draw it that way. Inner and outer. So let's try to do 1 inner, 1 outer for each of these. So let's do the inner first. So the inner in this case is a little bit weird, but it's okay. The inner again is always top minus bottom of just the connector. Looks like it's going to be the x-axis minus the line negative 2. There's no involvement of the functions themselves. So it's going to be 0 minus 2. And then the outer is going to be top minus bottom of the entire object. So outer. So top minus bottom of the entire object. Looks like the top function is going to be y is equal to the square root of x. What is the top of this object literally touching? And the bottom is going to be this rotation axis. So it's going to be the square root of x minus 2, which is the square root of x plus 2. So there are sometimes minus actions when you have these negative rotation axes. So then that's it for that one. Let's just do the same thing for this half of the region, but with a different line, of course. So the inner actually is the same. Notice it's going to be 0 minus 2 again. So it's going to be inner is 0. We can write plus 2 this time because we're simplifying that minus. Finally, what's the outer? The outer is top minus bottom of the entire object. This rectangle and this connector perceived as one object glued together. So it looks like the top is going to be this function right here, negative x plus 6. So negative x plus 6. And then the inner is going to be minus, or not the inner, but the bottom is going to be minus 2. So it's be plus 2. So again, it's top minus bottom. So we had 4 top minus bottoms in this case, but hopefully you see where I got all my information. On this side, top minus bottom for the inner, top minus bottom for the outer, so it was square root of x plus 2. On this side, it was top minus bottom for the inner as well, but top minus bottom for the outer was square root of x plus 2. So now we're ready for the answer because we can just form the question. So the answer again is going to be 2 integrals. I'm going to write them one on top of each other because I don't have enough space, so sorry about that. But it's going to be the integral pi, let's not forget a pi, and then it's going to be outer squared minus inner squared. So in this case, it's going to be square root of x plus 2. Let's see if I can squeeze this in. Looks like I can. Then it's going to be 0 plus 2 squared. Don't forget the squares. Don't forget the pi's. Often people miss those. Then the next one is going to be pi times the integral of the new outer squared minus the new inner squared. We already found this information, so we should be good to go. It's going to be negative x plus 6 plus 2 because it was minus 2 again. We're going to wrap this all in parentheses. and square it. Don't forget the squares, don't forget the pi's. And then we're gonna write minus 0 plus 2 squared dx. Now all we have to do is determine the endpoints, but again, remember that the endpoints do not matter about this at all. It all matters about the region itself. So the first region went from 0 to this intersection point, so that's going to be 4. So this would be 0 to 4. And then for the second region, it looks like we went from this intersection point all the way to the endpoint, which is going to be 6. So this would be 4 to 6. So that's how you do washers. Again, this process is pretty lengthy and it takes a long time to explain. But once you get the process down, every single question becomes the same. They can't really trick you at all with these questions. It's always integral of outer squared minus inner squared with a pi in the front. Outer is top minus bottom of the connector and the rectangle as one object. Inner is the radius of the inner is going to be just the connector. Top minus bottom of just this connector. And if you just do a lot of these questions, you should be able to master this because again, the process is the same, the steps are the same. So if you want more practice with this, I perfectly understand. What I'm gonna do is I'm gonna link our normal Girls Teach Calculus video to the description of this video so that you have more time to practice. One of my former students goes over several of these examples. She practices ones where the rotation axis is this way, the rotation axis is this way, she does this, she does washers, and so on. So be on the lookout for that. Check that out if you want more practice with this. But hopefully this video was useful for you in learning how to do volume by rotation and revolution. If it was, please give us a like and subscribe. It definitely helps us out. But no matter what, hopefully I'll see you in our next video where we do volume by cross sections, which is a fairly similar process. And no matter what, thanks again for watching this video, and I hope to see you next time.